Well, it's my pleasure to welcome you all, in particular, of course, David Aasen, who's giving us an invited presentation here, and us, that's actually here, the hybrid quantum programming course here. And also, actually, it's a COPLAS talk. This is Copenhagen Programming Language Seminar talk, and also a DIREC talk, which is and Thomas is the head of DIREC is also present. Thank you for joining, Thomas. And what I'll do here is just very briefly say about way fewer words than I should about David, and say that the talk we have here is part of our course, but it's also a public presentation on quantum software-related aspects that DIREC is coordinating and organizing this year and next year. So welcome you all. And David, first of all, of course, thanks again for joining us on short notice, and apologies to both you and to all the other members who might actually be interested in getting this talk and seeing it live, but we'll record it, and with your permission, and later I'll explicitly make sure we get that one, posted in various places. In particular, I hope at DIREC, who will make it available then through the quantum software community. So David has been with Microsoft Station Q, as it's called. You can maybe comment on that one later or not, for a while, but previously actually his PhD as a physics in physics, I should say, in condensed matter physics at Caltech. And he's worked as a postdoc and then a joint postdoc originally at Pauli, I think that's how it's pronounced, Institute, and and at Microsoft. Now, presently, he works full-time at Microsoft, as I mentioned, Station Q, and specialty, a number of specialties, but is actually topological coding and the quantum programming and quantum computing, I should say, in connection with the magnet computer also. So I'm saying this here because we're in Denmark. I know you were doing with Microsoft and Atom Computing other projects too, but this is a big project, and I hope also for all of us here in Denmark. So welcome again, David, and we're actually all looking forward to actually hearing you. Thanks.
Perfect. Thanks very much for the kind introduction, and thanks so much for inviting me. It's really, it's always a pleasure to talk about quantum error correction and exciting developments in this field. So really look forward to that. Feel free to interrupt me at any point to ask questions, anything you like. Happy to dive deep into any topic. So today I'll be talking about...
Stop. Sorry, I forgot to start the official recording. If we could just do me a
No
favor.
problem.
Pretend like you started start again after you hear this recording part. And I do apologize.
No problem.
He just cut it.
Well, let me do this again because I want to make sure that we get a separate recording of only your presentation.
Okay, yeah.
That I don't have to post edit. You have no idea how difficult it is with my software. So I am presently recording, it seems.
Yes.
So I'll stop the recording, and while everybody's watching, and I feel sort of like, what is going on? I should. I'm trying to stop the recording completely. No. Sorry, because then I have to post edit it. You know what? I'll have to do that. So
I could easily do that.
yeah. Okay, we'll start the recording again. Sorry about that.
No problem. We're good to go. Thank you. So yeah, thank you, Fritz, for inviting me to give this seminar. It's a great pleasure to talk about recently completed work here at Microsoft. So you can look for more detail in these two references shown at the bottom of the slide. And let me just confirm, do you guys see my pointer?
Yes.
Excellent. Okay, so today I'll be talking about this topic, fault-tolerant computation with four-dimensional geometric codes. And the story here is, well, 25 years ago, Dennis Landell Kataev Preskel introduced the four-dimensional loop-only Tor code, which is very interesting. It has very exotic properties, such as the single-shot property, which I'll talk about later. But the qubit overhead was prohibitively large. Also, it lives in four dimensions, so it wasn't exactly clear how you could realize it in hardware. Now, we solved one of those problems by using this idea of geometric enhancement. So we rotate the lattice to cut down qubits. Think of like cutting the corners on a torus in order to cut down qubits. And then, of course, we use modern hardware, which allows all-to-all connectivity in order to actually realize that code in practice. Okay, so in the last, well, of course, there's been many developments over the last 25, 30 years in quantum error correction, but I wanted to highlight two developments in the last 10 or so years on this slide. So in the last 10 or so years, we've seen several hardware modalities appear which enable all-to-all connectivity. And of course, they're not just the ones shown on this slide, but these are the ones I'm focusing on. So for example, here is Quantinuum. This is their H2 racetrack processor. I believe it has 56 qubits. Now they have moved on to their next generation of system called Helios, released, I don't know, a month or two ago, which is a 98 qubit trapped ion processor, both achieving world-class fidelities. So think around 3 nines of fidelity on the 2-qubit gate or higher. In tandem, we've also seen rapid developments on neutral atom processors as well. So back to about 2014, the Lucan lab showed that you could individually trap and move neutral atoms in optical tweezers. And then in the late 20 teens, maybe 2018, 2019, they demonstrated or showed a path to getting high fidelity 2-qubit gates. And then at the end of 2023, early 2024, they demonstrated this logical processor in this paper here. Along with, sorry, was there a question? Okay. Along with this academic lab, we've also seen many industry labs appearing, such as Atom Computing, Inflection, Quera, Pascal, and so on, which are all trying to develop their own logical processors using similar technology. Okay, so the highlight here is that in the last 10 or so years, we've seen several hardware modalities which allow all-to-all connectivity. In parallel, we've seen major advances in high-performance quantum error correction codes. So for a long time, we focused mainly on surface code, at least in industry, due to its nearest neighbor local connectivity. So this is the code you want to use for superconducting qubits, for example, although there are other ideas out there. In the last few years, there's been a tremendous focus on searching over and finding new codes which have a higher encoding rate and higher performance, so-called LDPC codes, which are now enabled by hardwares which allow all-to-all connectivity. Okay, so that sets the stage for the talk. Now what I'd like to do is review in some detail the two-dimensional Tor code. This will appear many times throughout the talk, and we'll use it as a reference for this four-dimensional Tor code, which is somewhat harder to visualize. So, and let me see if I can use a laser pointer, because I see my cursor keeps disappearing. Okay, perfect. So the two-dimensional Tor code, it can live on any cellulation of a manifold. In this case, the manifold is a torus, and the cellulation is just a square lattice. So we identify this right edge with this left edge, this top boundary with this bottom boundary. That gives you a torus. The qubits live on the edges of this lattice. So there's 2 qubits per vertex, for example. These stabilizers are as follows. So you have 1 stabilizer per plaquette. This is the product of poly Z around the boundary of a plaquette. And the poly Z operator is just, diagonal 2x2 matrix with 1 and -1 on the diagonal. The X stabilizer lives at each vertex, and it's given by the coboundary of a vertex, i.e., all edges which meet at that vertex each get a poly X multiplied by them. Now, one can check that, of course, when stabilizers of similar type will always commute. Stabilizers of distinct type will commute if they have non-overlapping support, but when they do have overlapping support, it's always on an even number of edges and therefore commute. The code space, the space you store all of your quantum information, is in the +1 eigenspace of all stabilizers. Now, one can check that if you were to multiply all stabilizers together, say all the z stabilizers together, you would get the identity. Similarly, if you multiply all of the x stabilizers together, you also get the identity. This means there's redundancy built into your stabilizers, and therefore you have some non-trivial code space to store information in. All right, how does error correction work in this system? Well, if you have a poly-z operator, such as those shown here, a string of poly-z operators will be detected by the X syndromes. So the vertex operators, which are products of poly-X, they anti-commute with poly-Z, and so a string of Z operators, or a Z error chain, will be detected by these vertex stabilizers. And that's the information that you will learn, from which you need to find a correction which removes this error chain. One way to do that is with so-called minimum weight matching. So here we search for the minimum weight correction, so minimum weight chain of poly-Z string that turns off all of the vertex stabilizers. And in doing so, you find this closed loop of Z's, which will be a stabilizer in this system. So yeah, this is going to be just a boundary of a product of a bunch of plaquette operators. Now, where we can get into trouble is if we apply a correction, but we don't choose the shortest path, but we choose the long path, or our error chain is too long, so that the shortest path turns out to be a non-trivial cycle on this torus. Okay, and that would correspond to a logical fault, which would be a true error. So those logical operators are the non-trivial, or correspond to non-trivial cycles in this torus. One is given by any path, any direct path on this lattice by a product of poly z along that path. So that's a non-trivial z-logical. Its conjugate x-logical is a non-trivial cycle on this torus living on the dual lattice and a product of poly x on all the edges on that dual lattice. All right, so often it's useful to record the code parameters as a summary of the quantum error correction code. The typical notation is to use n in the first entry for number of qubits, k in the second entry for number of logical qubits, and d in the third entry for the distance of the code. And if you have a distance d code, I should mention that you can correct roughly d over 2 errors before you'll incur a logical fault. For this two-dimensional Tor code example, we have, in this case, it is a d by d torus. So there are d squared vertices, and since you have 2 qubits per vertex, there are 2d squared qubits. There are 2 logical qubits. I've shown the conjugate logical operators for a single one of them here, the x and z. If you were to rotate those operators by 90 degrees, you would find another pair of logical qubits. And the code distance for this code is simply d, just the number of edges in the shortest cycle. Are there any questions at this point? Great. Okay, so now the two-dimensional Tor code has it has fantastic properties, actually. There's many things we love about the two-dimensional Tor code. One thing we don't like about it is that it has a relatively small encoding rate. So if you take the ratio of number of logical qubits to physical qubits, this is going to be 1 over d squared, which as the distance gets larger, you can correct more and more errors, you can get lower and lower logical failure rate, but your encoding rate, the number of logical qubits that you get out of the system, are quite low. So what I wanted to do is discuss what are the types of design considerations that one takes into account when designing quantum error correction codes for a particular hardware. So the first thing you do is consider the inputs. What is your hardware? Are you dealing with trapped ions, such as in this racetrack processor, neutral atoms, such as you find in Lucan's lab or atom computing and so on? defect centers in silicon? Do you have photonic-based qubits? There's a bunch of flavors of qubits out there. What kind of hardware and qubit are you dealing with? Next, you consider what are the primitive operations? So do you only have CZ, Hadamard, and measurement in the Z basis, or is it natural to have C naught, Hadamard, and measurement in Z basis? Or maybe you have pairwise measurements across your qubits, such as in a Majorana-based system, or in a photonic system, you might have simply Bell measurements and preparations of resource states. So what are the primitive operations in your hardware? The next consideration is what kind of noise model do you have? For example, you might have highly biased errors, which is something that we could take advantage of on the quantum error correction side. Or you may have loss, such as in neutral atoms, you can lose atoms from tweezers. Or in a photonic-based system, you can lose photons. They can escape the fiber and the information is erased. Or in a solid-state system, you could have defective components. Certain qubits may just not work, and this is something you have to account for on the quantum error correction side. The next thing you consider is more of an industry side comment, which is what is the target application? What are you trying to do with this quantum computer? Are you trying to do chemistry? Are you trying to factor large numbers? Or maybe you're trying to do a demonstration. Maybe you're trying to make a high fidelity Bell pair. Maybe you're trying to show some short Clifford computation. There's a number of applications that you might consider. Once you know the given application, the hardware, and the error correction code, then you can design to the number of physical qubits that you need. And in the next few years, it's natural to consider numbers like 100, 1,000, 10,000. All right, so once we've considered all these inputs, then one wants to design your quantum error correction code, ideally with the following properties. So you want to maximize the encoding rate. So this, for the two-dimensional Tora code, was 2 logical qubits per 2d squared physical qubits. So it's 1 over d squared, which is going to 0 as d gets large. Ideally, we could find, but of course, we're also building a finite-sized quantum computer, so that's fine, so as long as d is not too big. But in any case, you want to maximize the number of logical qubits per physical qubit. Next, you would like to minimize the logical failure rate. A good proxy for minimizing the logical failure rate is to find codes which have a high code distance. Recall, the code distance tells you roughly how many errors, primitive faults in the system that you can correct. Typically, high encoding rate and high code distance are in contention with one another. For example, it's very easy to find codes which have very high encoding rate, but also have low distance. Similarly, it's easy to find codes that have very high distance but low encoding rate. Maximizing both of these is hard and produces an interesting trade space. Next, you want to consider your logical cycle. What is the logical clock in your system, especially when you consider the given target application? So for example, in neutral atoms and ions, the timescales are typically microseconds to milliseconds. Whereas in solid state systems, you can get down to nanoseconds to microseconds. And so in a solid state system, like superconducting qubits, you may not care too much about this efficient logical cycle. But in a neutral atom system or trapped ion system, you very much do. And so having this single shot property, which means you can get away with 1 round of error correction rather than D, is very favorable. And we'll get into that later today. Lastly, you want to maximize the computational space-time volume. So the set of logical operations, the amount of compute you can do, you of course want to maximize. In some sense, all 3 of the previous bullet points also do that, but there's one bullet point that's not captured, which is how you do logical operations in the system and how they compile into the actual circuit that you want to perform. So having an efficient compilation of logical operations is very important. So the code I will discuss today is this 4-dimensional geometric code based on the loop-only Tora code, and it hopefully I can convince you that it ticks all of these boxes. All right, So let's review this idea of rotation. The first reference I'm aware of is from Wen back in the early 2000s, where he considered the Wen-Plaquette model, which is simply a rotated torus code. So we started with this two-dimensional torus here, shown in the full square. And what one can do is rotate it in some sense. It's actually perhaps better to say we pick a different cellulation of that two-dimensional torus, which is determined by the two vectors which span its side here. So in this picture, what I want you to do is identify this upper right edge with this lower left edge, and this upper left edge with this lower right edge. Okay, so that defines a new cellulation of the two-dimensional torus. And one can then, again, compute the code distance in that case. And it turns out to be exactly the same as this outer larger torus. So the code distance of both of those codes is d. Because it's a torus, you still get two logical qubits. And because we have cut out these corners, or chosen the smaller inner torus here, we have halved the number of qubits. Okay, so 2d squared goes down to d squared. And so we've optimized one of our parameters. We've increased the encoding rate by a factor of 2 simply by considering this rotation. And so the key idea of this talk is going to be extend this idea of rotation to the four-dimensional loop-only torus code. So that will make this code very, very practical. And then it turns out when you, well, there are many rotated codes in 2 dimensions, but this is the optimal one. In higher dimensions, you get a huge space of rotated codes, and you can optimize over all of them, and I'll discuss some details about how we do that. All right, so what is the four-dimensional loop-only torus code? Well, in this case, of course, just like the two-dimensional torus code, it can live on a cellulation of any four-dimensional manifold. In this case, we'll take the four-dimensional manifold to just be a four-dimensional torus. We will also take the cellulation to be this four-dimensional hypercubic lattice, which I'll probably just call a cubic lattice in 4 dimensions. So the way I'll draw those pictures, well, we'll have 4 axes because we're in 4 dimensions. I'll label them 0, 1, 2, and 3, or sometimes X, Y, Z, and W. I will draw 3 of those 4 dimensions in, 3-dimensional pictures, such as shown here. And then the 4th dimension will go, off into the back of the PowerPoint, but it's still there, of course. Now, the quantum error correction code, it lives on this lattice. It has 1 qubit per plaquette or face. So all of these green squares are qubits, for example, and so are all the other ones. The stabilizers live on the 3 cells and 1 cells, and I'll go into detail in a moment. And so, for example, if you look at the 1 cells, these all correspond to syndrome measurements. And in this case, they are violated syndromes. So that's why I've highlighted them. So these are the analogs of the vertex terms we saw in the two-dimensional torus code earlier. And because of the single shot property of this code, those syndrome patterns always must form closed loops, which is pretty fantastic. And the analog of doing this correction, which was a string operator connecting the violated vertices, is now correcting with a two-dimensional surface or membrane whose boundary agrees with that loop syndrome pattern. All right, so it turns out you can have those properties in higher dimensional torus codes as well. It's just the fact that in 4 dimensions is the first place that this happens. So if you were to go to higher dimensions, what happens is the stabilizer weight increases linearly with a dimension. So the number of polys appearing in a given stabilizer is the weight, and that increases linearly with the dimension. And when you go to infer or measure those stabilizers, they're composed of mini primitives, a bunch of CNOT gates, and a pair of measurements. And so as your stabilizer weight increases, you become more and more likely to introduce a fault during the measurement. So typically we want to keep stabilizer weight as small as possible. All right. And that's why I went to 4 dimensions. It's the first dimension where you're single shot, and it has the lowest stabilizer weights. Okay, so here's a little more detail on the 4-dimensional toric code, viewed through this 5-term chain complex. So this is the chain complex of the 4-dimensional cubic lattice. There are 4 cells, which kind of look like this tesseract picture. There are 3 cells, which are volumes, if you like, or cubes. So those each are identified with 3 coordinate axes, for example. And then there are 2 cells, or plaquettes, which are labeled by 2 coordinate axes. There are 1 cells, or edges, and there are 0 cells, or vertices. Okay, so typical CSS, quantum error correction code, uses a 3-term chain complex. We would put Z stabilizers on one term, qubits on the next term, and X stabilizers on the last term. But it is helpful to use a 5-term chain complex because these outer 2 terms, C0 and C4, will record redundancies in our stabilizers. So for example, the Z stabilizers, which live on the cubes, have redundancies coming from the hypercubes. Similarly, the X stabilizers, which live on the edges, have redundancies coming from the vertices. In particular, if you look at the 8 edges coming out of a given vertex, each one of them corresponds to a stabilizer, and if you multiply them together, you get the identity in the absence of error. All right, so let's see how all of that unfolds. So here is a cube. This is where the Z stabilizer lives. Recall qubits are on plaquettes. If I take the boundary of a cube, this corresponds to 6 2 cells, or 6 plaquettes. Each plaquette gets a Z on it, and that defines our Z stabilizer. Similarly, each X stabilizer corresponds with a single edge. If I take the co-boundary of an edge, which is just all of the 2 cells which meet that edge, that defines the X stabilizer. So you put a poly X on every 2 cell meeting at this edge. Now, because a boundary of a boundary is 0, you are guaranteed that these X and Z stabilizers commute. All right. So, as I said earlier, if you look at a vertex, there are 8 edges that come out of it, as shown on the right here. And for each edge, there is an associated X stabilizer. Now, if you multiply those X stabilizers associated with those 8 edges together, you will get the identity in the absence of error. So if you look at a given syndrome pattern and you see that you do not have the identity, that indicates that some error has occurred. And in fact, it indicates a measurement error. And that's what's depicted at the bottom of the screen here. So most of the time, so if you were in the absence of error, everything would be closed loops. But if you have a measurement error, then those closed loops turn into segments. So that's what's represented by this dashed line here. And we see that by checking the X redundancies. So if we multiply all of the syndrome values exiting from a given vertex, at this vertex it'll be non-trivial, at this vertex it'll be trivial, and so on until we get all the way around the loop and we see a non-trivial vertex syndrome here. Okay, so stabilizer redundancies are very important, and what they allow us to do is to perform a two-step decoding procedure. First, you match the endpoints. So if you you find all of the violated vertices, you perform minimum weight matching on them to correct the measurement errors, very similar to what we did in the 2-dimensional toric code. And then what you'll be left with is a soup of closed loop syndrome patterns, and you perform minimum weight membrane matching on those closed loops. Any questions at this point?
We're hanging it.
Great. Yeah, sorry, just grabbing some water. Okay, so now I'd like to turn back to this idea of rotation. I'll describe it in a fairly general way in 2 dimensions, and the extension to 4 dimensions will be clear from that. Okay, so this is 2-dimensional toric code again, and a general rotation. So we start by taking the integer plane, so 2-dimensional coordinates with integer parameters, and we pick an integer lattice. So L is an integer lattice specified by 4 integers, A, B, C, D. The rows of this matrix L are the lattice vectors V0 and V1, which we would like to quotient by. So that quotient just means that if we have an integer coordinate xy, it's identified by xy plus V0, and also with xy plus V1. Then we pick a set of representatives in this quotient, and that defines our lattice. A useful picture is shown on the right here. So we have the integer vectors, V0 and V1, that we're identifying by. So this is why this upper right edge is identified with this lower left edge, and this upper left edge is identified with this lower right edge via V1. The integer lattice in this case is just 3 minus 3, 3. And the set of vertices, edges, and plaquettes, which appear in this white region, are the representative coordinates. Now, different lattices will give different cellulations, so you can tilt this and so on, and find different representative set of points for the same quotient. All right, so here's another example. We take a lattice L, which is just this integer matrix. One can change bases by adding and subtracting vectors together, as shown here. So these 3 matrices all represent the same integer lattice. So if you were to look at translations by any pair of vectors that you see in these 3 matrices, you would find the same set of orange dots, which are the integer lattice in this 2-dimensional coordinate plane. Similarly, for each one of those matrices, you can pick a unit cell for which you record all of your representatives, and they will all give the same quantum error correction code, perhaps up to a relabeling of qubits and stabilizers. And so later, when we do a search over quantum error correction codes, we will want to quotient by that degree of freedom as well. We don't want to perform an exhaustive search over all possible lattices or all possible codes which have the exactly the same set of stabilizers. And so the way we do that is using the so-called Hermite normal form, which is a unique representative for every integer lattice. And it's given by the following. So you have an integer lattice specified by, in this case, an n by n matrix. The Hermite normal form is an upper triangular matrix with positive entries along the diagonal, and entries on the upper part of this triangular matrix are all positive as well and sit exactly between 0 and the diagonal element. Okay, and again, the rows of this integer matrix span the lattice. Okay. Similarly, when we go to do code search, it's important that we can count degrees of freedom because we want to minimize the number of physical qubits for a given distance, for example. And so this is how we do that. So notice that each unit area in this 2D square lattice corresponds to 1 vertex. And so if we can count the unit areas, we can count the number of vertices. And if we can count the number of vertices, we can count the number of plaquettes and qubits as well. Okay, so then one just needs to figure out how many of these unit areas fit into this unit cell. And that is, of course, just the ratio of the area of that unit cell to the unit area here. So the area of that unit cell is just given by the determinant of the lattice. That's the volume form. And so therefore, the determinant of the lattice tells you exactly how many plaquettes there are. It tells you how many vertices there are. And if you know the number of vertices, you can count the number of qubits. That's because there are 2 qubits per vertex in this case, and so there are 2 times the determinant of the lattice number of qubits. All right. Now, in this case, in the two-dimensional toric code, the code distance is given by the so-called L1 systole. So this is the length of the minimum cycle in this torus, where length is measured in L1 norm, or just Hamming weight. All right, so that's the code distance. When we want to do code optimization, we can now just simply enumerate all Hermite normal forms for a fixed determinant, and then maximize the L1 systole at a fixed determinant to find the optimal code parameters. In this case, it would be twice the determinant of the lattice that optimizes those parameters. You get 2 logical qubits because it's a toric code, and code distance d given by the L1 systole. Now, when we consider the other design criteria, we may want to optimize for them as well. For example, certain lattices may be more symmetric and lead to more logical operations. Okay. And Fritz, can you remind me how much time I have?
You have another 10 minutes.
10 minutes.
If you
Okay.
need more, please.
Okay, good. I might take a little extra time, but people should feel free to leave. I won't be insulted. Okay, so now we're getting to the 4-dimensional loop-only toric code on a rotated lattice. So we're living on this 4-dimensional lattice and or 4-dimensional torus. And so the first thing to ask is, how many logical qubits do you have? Well, one can check that if you take a coordinate plane, say in the infinite volume, a coordinate plane where you multiply by poly x along all of the, or sorry, poly z along all of those plaquettes, that will commute with the stabilizers. And similarly, if you take a dual coordinate plane and multiply by poly z on those dual plaquettes, that will also commute with the stabilizers. So we get 1 logical qubit per coordinate axis pair. So in this case, 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3. And that still holds when you apply rotation in 4 dimensions to a rotated torus specified by this 4x4 Hermite normal form here. The reason that's still true is it's simply just another cellulation of the 4-dimensional torus. So you get 6 logical qubits. Now, in 2 dimensions, we were lucky. The code distance was simply the L1 systole. In 4 dimensions, it's not so simple. One actually has to compute the code distance by, for example, exhaustively enumerating over all possible vectors until you find one of minimum weight that commutes the stabilizers, but is not in the stabilizer group itself. So that's an expensive process to do. But what we observe numerically is that every optimal code, meaning code that achieves optimal distance for a given determinant, also achieves an optimal L1 systole. And so when you go to larger systems where you cannot exhaustively enumerate all codes and exhaustively compute all code distances, one very good thing to do is to filter codes by L1 systole in 4 dimensions. So maximize L1 systole for a given determinant, and then in that much smaller set, you then compute what is the code distance. All right, so this is what we find. There are many examples here. So I'm increasing determinant from top to bottom. I'm recording the number of qubits, which is in this case just 6 times the determinant of the lattice. That's because there are 6 qubits per vertex. The number of logical qubits is k, which is always given by 6. And then the code distance just has to be computed numerically, and I've recorded it on the right here. Okay, for comparison, at the bottom of the screen, I've shown the unrotated 4-dimensional toric code and recorded roughly, there aren't exact matches between top and bottom, but roughly the qubit savings that one gets by the rotation. And notice that for the determinant 45 code, which is distance 15, which is most closely compared to the L equals 4 unrotated toric code, you save about 5.7x in qubits. This should be contrasted with what we saw in 2 dimensions, where we save at most a factor of 2. So in higher dimensions, you can really save a lot. And we conjecture that if you were to look at the full family of 4-dimensional loop-only Tora codes and find the optimal one, that one would find a 6x reduction in qubit count. All right, in the interest of time, let me go brief here. So for every for every stabilizer code, if you want to run it in practice, you need a syndrome extraction circuit. We found one that occurs in 8 layers, which is very efficient. And in the case of neutral atoms, you can lose qubits, so it's very important to introduce some loss tolerance into your circuit, so you can actually correct for errors. And this is a simple gadget on the right here, which will actually do that for you. And if you were to look at the circuit, what one finds is that in finite time, every qubit gets measured. Okay? Typical syndrome extraction circuits, only the syndrome qubits get measured, but in a loss tolerant circuit, every qubit has to be measured in finite time. All right. Now, with that, once we have a syndrome extraction circuit, we can do performance simulations. So what's shown on the right here is relay BP decoding of this 4-dimensional loop-only Tora code with a small window size, in this case 3. So we include 3 rounds of syndrome extraction into our decoder. Because it is single shot, because the code itself is single shot, it is okay to just include 3 rounds. If one were doing lattice surgery-based Tora code, one would have to use D rounds, for example. And this is what we find. So the green line is this determinant 3 lattice, relatively poor error rate. The dashed line is the logical failure rate for the trivial code with 6 qubits, i.e. no stabilizers. So that's like a baseline reference. And then these orange and blue lines are both the Hadamard lattice, which is this determinant 16 code that we saw earlier, but I didn't highlight. Let me go back to it. So this is the Hadamard lattice here. It has 96 physical qubits, 6 logical qubits, and distance 8 appears in this line here. That lattice is great because it's highly symmetric, and so it has lots of logical operations. And this slide shows that it also has very, very good performance. So the blue line is showing, roughly 3e minus 6, 4e minus 6 logical failure rate per round. And if you introduce bias, Z bias, into the model, you can gain another order of magnitude on the logical failure rate. At the bottom of the slide, I show a comparison with other leading codes out there. So here's the rotated surface code. It performs very well, but it has a low encoding rate. The bivariate bicycle code, I picked a code that has roughly the same distance as 4D Tora code, and we see similar logical failure rate. The ship's code at the bottom has slightly higher logical failure rate, but actually it has very, very efficient synthesis. So that's another trade-off that one can consider. And on the right here, I just want to highlight that the pseudo threshold of the 4D Tora code is very, very high, which means, that's something very convenient because that's this is the point at which it's better to use logical qubits rather than physical qubits. Of course, there are caveats here with the physical noise model and so on and so forth. But the higher the pseudo threshold, the sooner you can start to actually use the code in an actual practical system. Okay, so how do we do logical operations in the system? Well, they come in 2 flavors. So one are these fold transversal operations, first introduced by Brookman and Burden back in 2024. So fold transversal comes in 3 flavors. One is a permutation, which, this is just a permutation of the qubits, which preserves the stabilizer group. So it's a symmetry. The other is a fold Hadamard, which is basically a permutation plus a transversal Hadamard. And the last is a fold S, which is a product of control Z gates, potentially non-locally across the lattice, along with S gates on a certain subset. And the way we find these is by defining a four-dimensional crystal, where the crystal is colored by the data qubits, and the ancilla qubits. It's three-colored. You have X ancilla, Z ancilla, and data qubits. And by studying the space group symmetry of that four-dimensional crystal, one can derive these fold transversal operations. Okay, we then go and simulate them. And what I've plotted here is the reference of the logical failure rate you gain by using a logical operation relative to the trivial logical operation, the identity gate. And so one can see that you roughly gain, in the worst case, a factor of 3 over the identity gate. Now, so these transversal operations are very efficient. However, they are not Clifford complete. So in order to get a Clifford complete set of operations, one has to use lattice surgery, which here we're showing a generalization of the usual lattice surgery to toruses. So the basic idea here is you take a pair of toruses, each specified by an integer lattice, you embed them into a larger torus, perform syndrome extraction on that larger torus, and then unglue them by performing syndrome extraction on the split torus. Okay, and that turns out to measure certain logical operators, and that Clifford completes the gate set. All right. Now, it's also important how well you Clifford complete the gate set, and that's the so-called Clifford synthesis problem. Given a generic Clifford state or Clifford operation, how do you decompose that into your logical primitives? On the x-axis here, I've measured logical primitives, number of logical primitives needed to reach a given target Clifford operation in error correction cycles. But you can also just read it as number of logical primitives. And what one finds here is that in the worst case, you need to apply 9 of our logical primitives. So for example, 9 transversal operations or some subset of transversal operations in lattice surgery in order to realize an arbitrary Clifford operation on 2 blocks. And in the typical case, you need about 5 to 6. All right. So with that, let me conclude. So we went out and searched for this block code with the idea of optimizing it for neutral atoms and trapped ion systems. We wanted a high rate code, so many logical qubits per block, so that we minimize the number of physical qubits in the system. But we balanced that with finding codes that also had efficient logical operations. So logical operations that were efficient to synthesize and also had the single shot property and very good error correction performance. So let me conclude by saying, it's a very exciting time in quantum error correction. There's lots of hardware modalities coming on online these days, and lots of very interesting trade spaces to explore and optimize over. So with that, I'll take any questions.
Thank you.
Can I ask a question?
Of course.
Yeah. So it's my understanding that you are essentially making a trade-off between de-round error correction, so like this extra dimension in time by some extra d factor in space, let's say. But this is a 4D code, it's not really a 3D code. So you're adding two dimensions on top of the 2 dimensions already in the toric code. So in that sense, I'm actually just curious what's the intuition behind it. As in, you achieve single shot error correction by adding 2 other dimensions rather than a single one.
Yeah. So I never really thought about it as replacing the D rounds with the extra dimension. That
The
might be
intuition might be
right,
wrong. I'm not sure if
but
it's
I mean,
correct.
yeah, I've just never thought about it. That might be right. I just haven't thought about it. I personally, I just thought about it as a property of this chain complex. So if I go back to that picture, where is it? Uh, here. Here. So, it's just you have a five-term chain complex, and as long as you have extensively many, points in C0 and C4, one will get stabilizer redundancies, which could be used to correct measurement faults. And so, you could go and look for single shot codes just by searching over chain complexes, for example, which have that property. Um, there's also different performances of single shot. Like, there are codes where C4 and C0 are not extensive, but there are still elements there. There are, you always have something there. I mean, this also encodes how many logical qubits you have in the two-dimensional Tor code. The product over all the plaquettes in 2D Tor code was one redundancy, and so there is one element sitting in sort of the higher part of this chain complex and one element in the zeroth part in the case of 2D Tor code. But yeah, interesting question about relating single shot to replacing D rounds in each direction with 40 lives. I hadn't thought about it, so yeah, I don't have a great answer there.
All right, thanks. That said, can I ask something else?
Sure.
Are these Z stabilizers, these redundancies, are they higher weight than the X redundancies? Or maybe I'm misinterpreting this chain complex, but I'm not sure.
They are the same weight. So
They're the same
there's
weight. Okay.
few ways to see it. So well, in this boundary term, there are 6 faces on the boundary of this cube, so weight 6. On the co-boundary of an edge, there are again 6 two cells, so again weight 6. Another way to see it is you have a duality between 0 cells, 4 cells, 1 cells, 3 cells, and 2 cells back to 2 cells. And so that gives you an exact mapping from your X stabilizers into your Z stabilizers. So that's another way to see that they have the same weight.
Okay, yeah, I see. Thanks.
A very basic problem or question is why four-dimensional geometric codes? I mean, one of the motivations was that they're viable because you have all-to-all communication, and maybe the answer is already given here. But what about high dimensions? Do they
Yeah, so we also looked at. Yeah, it's a very interesting question. So, and there's multiple reasons why it's interesting. So of course, the one fallback that you get in higher dimensions is you have higher stabilizer weight. So you record your syndrome patterns with lower fidelity. But if the code is very high performance, that may be worthwhile. And actually, we didn't simulate these higher dimensional codes, so that's a very interesting idea, and one should go and check. The other reason you might want to look at higher dimensions is, for example, in 6 dimensions, you get transversal non-Clifford gate. So for finding, a universal gate set, you may want to use higher dimensional Tor codes as well, and you may want to find ways to interface them with the lower dimensional Tor codes that have good Clifford synthesis properties. So it's a great question, and one should look into it. Did that answer your question?
Follow-up question? Yes,
Yeah.
thank you. Yeah, my homological algebra is a bit rusty, so actually never had it. So it looks like you're searching, combinatorially searching for good code there. Are there results that show there is no better way of doing this? It's like some of these code searches, NP complete or NP hard at least, so that or is there are there actually converseness for any dimension? Are these actually are there algorithms that will actually find good codes, or is this really inherently hard computationally in fact codes?
I think this is hard computationally,
but yeah.
Yeah, so well, there's a number of answers here, but one is it's definitely hard computationally. Like your computing code distance is exponential in D, polynomial in block size. So that's difficult.
Okay. Is it
Pardon?
inherently exponential? Sorry. Is it inherently exponential? Is it provably inherently exponential in the sense NP hard, or is it just best state of knowledge?
Yeah, so this is where it escapes my expertise, but it is probably provable. But it escapes my expertise, so I don't know. Um, the basic reason there is there's exponentially many bit strings to search over, and you have to find one that commutes with all stabilizers. Um, Now, the other reason it's hard to do like a very general code search. So one is distance is just hard to compute. But of course, at small distance, you can pay that exponential price. At slightly larger distance, you can use various solvers. But the other reason this is really difficult is it's really hard to find commuting sets of stabilizers. And that's why we go and use homological algebra, for example. If you start with a chain complex, you're guaranteed your stabilizers commute. If you just go and randomly pick, weight 6 operators from the poly group, generally they won't commute. And so it's even hard to just find stabilizers that commute with each other, let alone ones that achieve high distance. And there, I certainly don't know uh, what the complexity is, but it seems like a very hard problem. Also, a very interesting one. I mean, it would be great to run an exhaustive search over QEC codes. Um, and there are references like Code Tables is a website you can go to, codetables.de. And in many cases, the optimal codes are known, like up to around block size of 20. Exhaustive searches have been performed. But as you get larger and larger, this exponential kicks in and it becomes hard to find optimal codes. And so then one goes to ideas of topology and homological algebra, things like that.
So last question, and definitely most
Sure.
fuzzy one that I can come up with for now, which is from at the end, when you talk about what kinds of logical operations
Hmm.
you can implement.
Hmm.
It, it whether it would be useful to have basically bulk primitives, logical bulk primitives, instead of having individual qubit operations, or uh, having basically like in a parallel machine, you say like I have a primitive that says I'll do these things simultaneously. I do multiple things here because the in this case maybe because the error correction would be easier to do it for a whole bulk operation like a multi-control operation, or something even more general, as
Oh,
you already indicate, probably with the fold and
yeah. So
fold
I
S
was
and fold
so
H operations.
so one thing that we do is prepare Clifford resource states, for example. So what one does is you have this Ancilla block where you do a bunch of operations on it to prepare a given state, and then you use that state to insert it into your data block. So certainly ideas like that are considered. One also considers certain logical operations that can be combined very efficiently. So for example, a permutation is really, in some sense, it's just a relabeling of the qubits in software. And so those permutations can be applied for free and paired with any other logical operation. I'm not sure if that's exactly what you meant. One could also consider higher like control not gates, like a control. Well, of course, control not is a non-Clifford gate, but you could consider like a multi-targeted control not. Um, Problem is, it's not easy to realize that in practice. Um, so even like CCZ in neutrals is hard. Realizing it in like superconducting system, you would typically have to synthesize it out of a T and several 1 and 2 qubit gate primitives. Um, but if you were to hand me a hardware that had those operations, we would certainly find ways to take advantage of them.
Okay, well, thank you again, David. Thanks.
Thank you.